Hello everyone, and welcome to this exam tutorial. The idea here is to help you prepare for your upcoming examination, and especially for those students in automation engineering, and also for those taking production in automation systems, that I mean students in industrial management. This will be quite helpful for you. It's just an insight on what to expect and an idea of how to handle such examination type questions, basically. So having said that, let's answer this question. Write a Boolean expression and draw an equivalent function block diagram for the circuit diagram on the left. Also write a Boolean expression and draw an equivalent circuit diagram for the block diagram on the right. So here we have two diagrams, one on the left and the other on the right. A circuit diagram here and a function block diagram. But first we'll focus, for this video, we'll focus on the function block diagram and circuit diagram, and then we'll try to have a Boolean expression for this. There are two rules we should know here. First, we have to represent the various elements, and by that I mean all the contacts here, A, B, C, D, and even M, the output. We need to represent them in Boolean expression format. And then and also we also need to show the connection between A, B, and C, and D, and all the elements here. So like as in algebra, there has to be an operation that connects two elements together. For instance, A plus B, or A times B, or A minus B are in usual algebra. So now we have to show that here, and to do that, we will need to have two rules here. We say a normally open contact, NO, will represent them with just the element as we have here, without any slight changes. So for instance, a normally open contact will be A, as we have, and where is another normally? Here we have another normally open contact, D, and then we have F here, normally open contact, and then E. So these are ways to represent normally open contact alphabetically, just without any difference. But in the case of normally close contact, there's a slight difference here, and I'll show you what I mean. B is a normally close contact, but we don't say B. We don't write B. We just say bar B. It's called complement of B, or inverted B, and same applies for C here. Bar C. So these are ways to represent normally open and normally closed contact in algebraic format. So wherever you see this, you know what it means. Then the next thing is, how do we show the connections between all these elements? And by that we mean what's going to be the operation, the function that connects them together in algebraic format. Before we explain that, we need to know the difference between a parallel and series correction, because these are the two rules that we will use to analyze the circuit and to be able to show the connection between all of them. So series and parallel connection, how do we show that? Now let's assume there's a 24-volt power supply here, and then there's current passing from the source. There's flowing down this direction, and then it gets here and splits in two directions because there's a junction here. So there's gonna be a split here somehow. Then here, let's call this current I1, and let's call this current I2. So which means that the big I, which is the current from the main source here, the big I, is equal to I1 plus I2. So it's basically the sum of those two currents that makes the big I. And now and then I1 gets to this point and even continue to this point, passing through C. But the same I2 flows through B here and even pass to this point. Now series connection, the way to represent series connection or to identify series connection is when you have current passing through more than two elements, the same current passing through more than two elements. As we see here, I2 pass, assuming A is close here, I2 passes through A and also passes through B and still at this point. But then looking at the connection, the relationship between A and C, is it in series or in parallel? It's in parallel because we have I1 here. Sorry, I1. We have I1 here. And we know that I2 and I1 are not the same. So we have different current passing through A and C. And so A and C are said to be in parallel. I think that point is made quite clear. And we have it I1 flowing here. But I1 splits and moves down here. So we have here I3. And we have here I4. It sounds like an iPhone. Anyway, and then it passes through here I4, and then I3 continue here, but then they meet at this point again to form I2, to form I1, remember, here, and then it meets at this point here to form the big I, which means I1 and I2 forms the big I. One big family. Anyway, then, so in other words, we say I1 equals I3 plus I4. So now we can now distinguish between series and parallel connection. So with that now, how do we show them in algebraic form? We say series connections are represented with a product sign in mathematics, and in some cases it's used as dot, or in other places we use this to represent it. While parallel connection are represented with a sum sign or addition sign, and in this case we use this to represent it. But for the sake of this example, we're going to be using a dot sign. So we'll take this out and we use a dot sign. You could use a multiplication sign too, but I think I would prefer to use that dot sign. Now with this we can answer this question. So A and B are in series. Why? Because I2 and I2 is passing through it. So same current passes through A and B. So we can represent that in series. So we say A, I'll use another color to do this. So we say A dot B. Remember, product. So they are in series. Now, then we know that the there's I2 and I1 are not in series because they are not the same. Obviously, same current pass through here, but it's not the same current that passed through here. So this whole circuit here is in parallel with C. This whole circuit here is in parallel with C. So we say plus C. Now let's not forget that B is a normally closed contact, so we should have a bar here. Same with C, as we indicated initially. Now then we also see that there is a split here. I2 is not same as I4, so D and F are in parallel, but I1 is equal to the sum of I2 and I4, so I1 is in series with I3 and I4. So that means C is in series, and remember, series is dot. We use a dot here, or we include a bracket as well. But in mathematics, you know, if we take this dot out, then we also still mean the same thing. So I would say we use a bracket just to make it feel a little look more mathematical. Then we say D parallel, and that's sum plus F and close bracket. Now the whole of this network, where all this current dispersed and they all meet together to form I pass the same current that passed through E. So the same current I that flows through all this network is the same current I that passes through E. So E is in series with all this network, and by all this network I mean the whole of this equation is in series with E. And that explains that And then we say we have a final output here. How do we represent the final output? Simple, with an equality sign, equals to m. I'll write this even better, m. So now we have our final solution. So with this, we have an algebraic, Boolean algebraic expression for this circuit. In the next video, we will be talking about how to represent this in a function block format and something like this here over here. But until then, enjoy.